our engagement with international fusion efforts. As you can see, we are making every effort to work with talented scientists and engineers worldwide, driving innovation and moving boron fusion forward. And of course, this symposium is a wonderful opportunity for all of you to connect, exchange ideas, and forge new partnerships. I hope the next 4 days spark fruitful discussions and lasting collaborations. Finally, I wish the symposium great success and all of you a wonderful stay here in Nanfang. Thank you all. Welcome.
Now, let's invite our chief scientist of EN Fusion and the chair of the scientific committee of this symposium, Dr. Peng Kai, give us a speech.
Thank you, Nubin. Thank you, Nubin. Distinguished guests, colleagues, and friends, on behalf of the Scientific Program Committee, it is my great pleasure to introduce the academic program of this symposium. The theme of this symposium is proton-boron fusion as both a scientific frontier and a future clean energy pathway. Around this theme, the abstracts in the handbook represent a remarkably broad and ambitious research landscape. Proton-boron fusion nuclear physics, reaction cross-sections, alpha particle production, intermediate nuclear states, electron screening, spin polarization, and non-thermal ion distributions, hydrogen-boron plasma physics in spherical torus, field reverse configurations, dense plasma focus, and laser-driven high-energy density platforms. Advanced diagnostics for charged particles, gamma rays, alpha products, boron concentration, fast current, eddy currents, and detector response, as well as modeling, materials, power conversion, medical isotope production, and proton-boron capture therapy. So this is amazing. This breadth, however, is essential. Proton-boron fusion will not advance through a single discipline alone. It requires precise nuclear data, controllable plasma conditions, efficient heating and current drive, robust confinement concepts, high rep rate, laser and beam facilities, integrated simulation, artificial intelligence, and credible engineering pathways to a useful energy. The handbook makes clear that our community is now moving from isolated demonstrations to a more integrated scientific framework. The 3.5-day academic agenda reflects this direction. The program features more than 40 invited and contributed talks, poster flash talks, a poster session, and an open rooftop forum on the critical path to making p-boron fusion practical, covering technology, economic, environmental, and regulatory questions. This is an amazing range of topics. We're honored to host distinguished speakers. Dimitri Batani, Eric Lerner, Liu Bing and Pang Danyang Massimo Alonso. I may butcher some names. Apologize for that. And Zhang Guoqiang, 10月江, G.A. Pablo Cerrone, and Kyung-Jin Cho from Korea, and Wudong, Jiangling Luo, 这是罗，对， and Ma Wenjun, Anton Morose, and Mohammed Amin Betty, and Edward I misspelled here, I'm sorry, Karudina, sorry. And of course, myself as a speaker, and many other leading researchers from universities, laboratories, institutions, and industry worldwide. I hope all participants will use this symposium as a genuine forum for open academic exchange. Please challenge assumptions, compare methods, share data, raise difficult questions, and build new collaborations across disciplines and countries. May these discussions clarify the physics basis, identify the most promising experimental path, and generate fresh ideas that advance proton-boron fusion from scientific possibility to practical application. I wish all of us a great success during this symposium. Thank you.
So now we start the first scientific session. Now our chair of the first session is Dieter Hoffmann, professor from the Jiao University. Please, Dieter.
Good morning, Mincheng and Martin. Thank you for this very nice introduction to this talk. And moreover, I like that you have problems with spelling out the names of the Western people. We make much more mistakes pronouncing your names. So my task now is very easy because I can easily pronounce it. The first speaker of this session is Professor Dimitri Batani, who is known as a leading scientist in our field. And I want to make one more remark. Those of you who want to submit a paper to the special issue of high power laser science and engineering, be very careful because the editor-in-chief will be listening to the talks.
Yeah.
So now we...
Peter, the first speaker is Martin.
Oh, I thought that was yours. Okay, this I can. So Martin, I don't have problems to pronounce your name. Don't mind, Martin. Hey.
We're all but human. Thank you very much. Let me proceed with the presentation on Boron11 fusion R&D at ENN. As Dr. Liu had already pointed out, some of the very important elements of the ENN fusion program. So I'm going to skip and hop as the view graphs would not duplicate. I would just like to say that the ENN Group is a growing company in many, many aspects, including the Hong Kong stock market. And we have these subsidiaries with stocks over there. The details I will not go over. And then the ENN Energy Research Institute, which started rather early. And now we're changing our names, but this is older style saying that it is an institute that performs R&D, forms research teams, and carry out state-funded R&D projects, and then create intellectual properties and create partners to work on fusion. Now, I'm going to spend a little time on this because this visionary goal for commercial viable fusion power actually has a very strong logic. Now, P-boron fusion, of course, we know is safe. It's aneutronic, especially if we can purify our boron-11 to how many nines? I think 6 nines, okay? Which is a technology, it will be accomplished in time. And it's tritium-free, and we all know the practical problems of tritium. And then it is also pollution-free. In other words, when we operate pure P-boron fusion, then it does not create a lot of pollution, nuclear pollution. So it is safe. Now, we always say, well, we have abundant fuel and so on and so forth, but what does it mean? It means that the fuel is accessible almost anywhere. And then it's suitable for widely distributed energy market. In other words, if we actually make the P-boron fusion work economically, it is not limited just to fusion energy. If you think about it, then of course, being a business, we have to seriously consider cost effectiveness. Well, ST in this case has a very compact fusion core. We know compactness, if it works, is related to lower cost. And because the fusion products are all in charged particle form, it opens up the possibility for efficient energy conversion. Again, energy conversion efficiency is a key element of cost. Now, low cost via economic of scale. You see, when we built the first, the second, and the third demo or proto reactors, they're not going to be cheap because it's a first of a kind device. But because this energy technology is distributable, meaning it could be placed nearby big cities, it could be placed, shall we say, in the highlands of Qinghai, and in such a way that it allows the economic of scale. We're not talking about in the future of building maybe just a few hundred reactors of different kinds. We're talking about thousands, tens of thousands. If it really works worldwide, hundreds of thousands of such devices, big and small. That's when the unit cost of each power source becomes low. And that idea is unique to P-boron-11 fusion. Okay, I've spent too much time on this. All I'm going to say, the spherical torus is a very different confinement configuration compared to the well-known tokamak. Instead of going into the detail, I'm just going to focus on 看得见啊，看不见，帮我把那个应该把那个红点拿出来，你会不会弄？激光哦，就是这个是吧？不是这个，是不是这个？激光 对，对，哎，好，谢谢你，老早就应该做了，对不起。So we know P boron 11 has huge challenges, but it has its advantages. We also know ST has its advantages, but it also has its own challenge. So the combination of ST with P boron, well, I have to say, in the field of fusion energy research, it is actually a unique and first of a kind combination. Let's see what it is. P boron 11 has the challenge because it has higher required triple product and it has intense bremsstrahlung. It's a broad spectrum X-ray emission, hard X-ray emission, or even called gamma ray emission, which penetrates everything and leaves the system, almost. But the advantage, of course, we said about P boron 11 is no neutrons, no blankets, the tritium breeding blankets and so on and so forth. But for the ST, it has the advantage of high beta, lower toroidal field, and more compact size, and the confinement time leverages R and B, but not IP. This is a fundamental difference from the tokamak scaling law. In other words, small increases in major radius leads to large increases in confinement time. Small increases in BT, the leverage is high, increased confinement time, but it is much weaker dependence on the increase on IP, which is the pronounced scaling of the tokamak. Now, it does have a big disadvantage. It has a limited space in the middle. So it is an engineering, technological, material challenge to put it in the middle and stay in the spherical torus configuration. So we have innovative ideas to raise the prospective feasibility of the P boron fusion burn. And Dr. Liu Bing will cover this. And the strategy that we follow here is that if we look at the top part is the high energy density physics, laser and particle beam platform, and proton boron fusion mechanisms. In other words, the fusion reaction mechanism itself becomes a really high leverage topic. And then if we look at the magnetic fusion, which spherical torus is one of them, and it has the options over here, including stellarator, but then hydrogen boron fusion plasma properties and its reactions in the magnetic confinement system with all of these different configurations is what we diligently work on. It's not limited to ST, not limited to tokamak, not limited. We take into account what the tokamak and stellarators can do in terms of the P boron confinement physics. And the end result is that we at the ENN R&D will progress in this way and eventually to the ST P boron power. Of course, that is our goal of demo. So I'm going to skip this, and I'm going to skip this, and just mention that Dr. Xie Zhang will discuss the progress that we have made in both EXL50 and EXL50U in an overview. I think it's tomorrow. And we've seen this, and what Dr. Liu mentioned about these high parameters is indicated here, and Dr. Xie Zhang will give the presentation. And also the high confinement mode. And here. Let's place the 1 megaamp discharge in EXL50U. What is the meaning of it in terms of our future development? And it's very easy to see that if you could see the ST development path. In other words, we have a very aggressive pathway in which we move from EXL50 to 50U and then to EHL2. In terms of the toroidal field, EHL2 is only 3 Tesla at the major radius. And we're talking about 20, 30, 35 time scale to lead to eventually what we call EXL3 class, which is much more significant, larger in such a way that it will produce significant fusion power. This is the plan. And some of the parameters are shown here with other STs. And also we put in our very important East tokamak at the ASIPP parameters for comparison. And what I would like to simply show here is the status of main engineering systems on EXL50U and future ST devices. Here is a indication or list of our heating systems that we have planned for EXL50U. And these are the diagnostics arrangement for that. And then for the future, we actually have an operating high temperature superconductor magnets. And that is the beginning of our effort to utilize operating high temperature superconductor magnets. And that is the beginning of our effort to utilize the technology advancements in this direction, which eventually will be needed for EHL3. And we also use AI-assisted plasma control. And we have posters on this, so I'm not going to get into the detail that we're learning AI control methods or AI-suggested plasma control methods that we're making great progress in this area as well. And we actually have a great plan for the use of AI, which is indicated here. And we will have a poster on this that will give the time and the detail for discussion. Here is a picture of the EHL2 design. You'll notice that this design is still a normal conductor design. In order to get to the duration of the discharge, overall discharge, which is many seconds, that we have chosen to use the liquid nitrogen pre-cooled design, which actually has a double cryostat or doer, and which makes the design sort of configurationally like East as well as ITER. And this gives us an opportunity to challenge our engineering and design and construction and maintenance and so on and so forth capabilities, which we believe is a necessary step in our capabilities that we jointly with our collaborators should have. On the right-hand side, I would like to simply to point out, it's a 3 megaamp spherical torus, 3 Tesla in the highest magnetic field on the major radius. And we're aiming to get to at least 20 kilovolt ion temperature, maybe even higher, and a confinement time which actually is as much as half a second. Now imagine that parameter set, if it can be obtained in such a small device, which compared to the standard large tokamaks, which is much larger, takes a lot of more difficulty to construct and build. And those learnings are very valuable for us as well. And the scientific impact on the whole magnetic fusion field is almost not estimable, but that is our goal. And it is tremendous goal. It has tremendous scientific and technological and material values. And then, of course, EHL2 is going to be built right next to the present EXL50U. And hopefully when you visit, if not already, you will see the big construction area that's already being set up. And on the right-hand side is a scientist rendition. And of what this facility is going to look like. And I think we have a poster on this that will show more detail. And with this, I'll simply say that we're looking forward to a collaborative growth, moving fusion energy forward with our partners. And here's a list of our collaborators nationally and internationally. And ENN is the first private company in China and the second worldwide to join the international tokamak physics and engineering activity, as already indicated by Dr. Liu. So this is our plan for the symposium, and I'm not going to dwell on this. And what I would like to say that we share the dreams and ecosystem of proton forum fusion energy. It's a dream for all of us. And EXL50U is going to be an open research platform for fusion. We're working diligently to make that possible, working with our collaborators. With that, I would like to say we would build the foundation, we would innovate, make breakthroughs, and realize clean, safe, abundant fusion power together. Thank you.
Thank you. Thank you, Martin, also for keeping the time, because we are a little bit over the time. So therefore, I would like to ask only one or two questions, and the questions are always short. Keep the answer.
The answer very short. Okay.
So, is there?
Thank you, Martin, for this comprehensive and still very clear presentation. I have a very short question. Which capital Q do you envisage for spherical tokamaks fueled with HV?
Capital what?
Capital Q.
Oh, capital Q.
Yeah, the gain.
For which device?
Spherical tokamak, the commercial version.
Well, it has to be close to 1. In other words, we anticipate auxiliary heating current drives always be there because it provides a control mechanism. And if you get to Q greater than 1, it's a runaway scenario. Okay, because it's pure charged particle fusion. So let me just say that my vision, my understanding or expectation is Q around 1.
Okay. Another short question.
The very nice talk and a very exciting talk. So I want to just let you compare the different tokamak parameters and include the EHL2. And aware the one of the parameter is the temperature, and the temperature is the same of other tokamaks. But the other tokamaks we use DT fusion. However, we need a higher temperature. What's your opinion on this temperature parameter?
Good question, and I agree. So EHL3 has to get to the range of over 100 kilovolt in the thermal parts of the plasma. And we haven't really gotten into this idea of suprathermal component plus thermal. Yes, we can discuss the detail of that. And it is also a totally different scientific plasma from the DT tokamak plasma basic operational conditions. Let me just at one point. For p-boron fusion to work, it is not by simply making a bigger, larger tokamak. We have to build a different kind of plasma to take advantage of the double peaks in the fusion cross-section.
Okay,
Thank you.
thank you.
Okay, Martin, one more thing. I expect the answer during copy or
Okay,
so
good.
you outlined the roadmap of ENN. What I want to discuss with you is what do you want to learn here, and what if you don't learn what you want to do? Do you have enough leeway for the next steps over coffee break or dinner?
I'm pretty sure there's enough leeway. We'll discuss it.
Okay, so now I already announced Dimitri Batani. He's well known in the field. And he will talk about the equation of state of boron nitride. I will give you a warning. Are you familiar with 8?
No,
Six,
just give me 5.
Okay.
So thank you very much to all of you, and especially to the organizer for inviting me to give this talk. It's really a pleasure to be here. So actually I'm coming from the University of Bordeaux, but I will mention that I'm also visiting professor at Peking University. And the work which I present is a result of a large collaboration. This list of authors is probably not complete, and you see that there are many institutions from Europe and from China. And I also would like to mention that a lot of this work has been done in the framework of the Cost Action, which is a European project supporting networking between groups on proton boron fusion, and also in the framework of the PKU ENN Technical Innovation Center established by ENN and Peking University. And we studied the question of state of boron nitride in extreme condition at very high pressure in different laser facilities, actually at the Pulse and the Lai facility in Prague, on the Shengguan 3 prototype in Minyang, and on the Gecko laser facility in Japan. So let's come to the why we are interested in the question of state of boron compounds at high pressure. Well, this is one of Dieter's favorite plots, which already tells you why it is interesting to study boron from the physical point of view. You know that boron is an element which is much less abundant than it should be, because indeed the proton-boron fusion reaction destroys boron inside the stars. So this is an important cosmological problem. But there are other, of course, many other reasons to study the physics of boron. Laser-driven proton-boron fusion experiment in the last years have shown very high yield of alpha particle generation. These are still very far from break-even, about a factor of 1,000 to 10,000 below break-even, but they can also be interesting on a shorter time scale to develop a new technology to produce bright alpha particle sources, which can be useful for many applications. And there will be several talks on this topic. And in the future, laser-driven experiment may imply compression of the boron fuel. And for doing this, we need to know how the fuel reacts to compression. So we need to know what is this equation of state. And from the point of view of the physics of material, boron nitride is very interesting because you see, by chance, boron nitride has, on average, exactly the same atomic number and atomic weight of carbon, which means that we expect the phase plane, the equation of state of boron nitride, to be similar, somewhat similar to carbon, with the important difference, of course, that on one side you have only one element, on the other side you have two elements with different ionization rate. So this comparing the equation of state of boron nitride to the equation of state of carbon is a key test for the physics of matter at very high density. And then it is interesting for SEF. As I said before, in the future, proton-boron fusion experiment driven by laser may imply the compression of the boron fuel. But even for the deuterium-tritium fusion, boron nitride and other boron compounds can be interesting. This is not our idea, it's an idea which is coming directly from the Livermore laboratory. And basically there are several reasons. One reason is that if you have an ablator, which is boron nitride, you can take advantage of the reaction from boron and nitrogen with the proton and the neutrons produced by the core at the stagnation time. And this can give you additional information. But also the mechanical properties of boron nitride can make it interesting to be used as an ablator. So actually these are some papers from the group at Livermore and Los Alamos proposing this use of boron nitride for ablator. And these are actually the technology which has been developed at the General Atomics to develop these kind of targets for laser-driven implosion experiment. Well, the main importance of boron nitride or other boron compounds for inertial fusion is related to the possibility of realizing implosions which are more isentropic than what is done today. Well, I imagine that you are all aware about the NIF demonstration of gain using DT fusion. And indeed, one important point in this experiment is that you have to use a laser path shaping, which is something like this, which allows a gentle compression at the beginning and then increase the pressure more and more. And indeed, this is important in order not to make the fuel too hot, because if it is too hot, it will be very difficult to compress it. Well, today's experiment use diamond ablator, and diamond ablator have been very important to achieve ignition. But there is a problem because in current experiment, this initial foot must be set at laser intensity high enough to produce a shock pressure of 12 megabar. Because at this pressure, we are sure that diamond will vaporize and will not recrystallize. So the idea now is to try to get a different ablator, e.g. boron nitride, which can allow to reduce the intensity of this laser foot so that you can get a more quasi-isentropic compression. So this is the reason why we want to study the equation of state of boron nitride. And actually, well, I go very quickly about this. There are not many experimental points for boron. Actually, there is one point obtained at the NIF laser facility. For boron carbide, there are a bit more points. And for boron nitride, there were, before our work, there were only 3 points established at the Omega laser facility of the University of Rochester. So that is why we started the work on boron nitride. And now let me explain quickly how you perform the measurement of the equation of state. Well, you use the laser to produce a shock which is traveling in the sample, so in boron nitride, and then you use a conservation law of mass, momentum, and energy across the shock front. And if you look at this equation, you see that there are 5 unknown, which are the density, the pressure, the internal energy of the material, the shock velocity. So sorry, but this pointer disappeared. Well, sorry, can you? The shock velocity D and the fluid velocity U of the material. So you have a system of 5 equations and of 3 equations and 5 unknown. So if you measure 2 equations, you will close the system and you will determine the equation state point of your material. Actually, what we do is something different. Sorry. Which is easier. Instead of measuring 2 parameters in the same material, we measure the same parameter, the shock velocity, at the same time in 2 different materials. One is boron nitride, and the other one is the reference material, whose equation of state is supposed to be well known, like quartz of aluminum. And to do this, we use well-established diagnostics, which are known as SOP, streaked optical pyrometry, is a diagnostic which looks at the target emission at the time of shock breakout, and the VISA, which is a diagnostic which measures the Doppler shift from a probe beam after the target is set in motion by the shock wave. Thank you very much. Okay. So the first experiment which we did was done at the Shenzhen 3 prototype, taking advantage of the equation of state platform which is developed there. And this used the so-called indirect drive as on the smaller scale, what is used at NIF. So we have a cavity which is called all-round. The laser beam are focused inside this all-round to generate a soft X-ray radiation, which drives the shock, which travels in the base of the material and then travels in the reference step and in the boron nitride steps. And these are typical results from the VISA and from, well, again, I probably touched something which I should not touch. So, well, from the VISA on the left and from the SOP, and you can see indeed the shock breakout at the base of the material on the 2 steps. And from these, of course, you can measure the shock velocity. And if you have a transparent material like quartz, you can also follow the evolution of the shock velocity in time, because quartz is transparent, so you see directly the reflection from the shock front in quartz. Well, we were using targets made in China and targets made in the UK with different characteristics. Actually, I would say that in general, the targets made in China were a little better because of the roughness of the material. And these are the points which we were obtaining in comparison to the 3 points of the equation of the omega laser facility. I should mention that boron nitride has 2 main allotropic phases, hexagonal boron nitride and cubic boron nitride, which are somewhat similar to graphite and diamond. And indeed, at the omega, they were using cubic boron nitride, and we were using hexagonal boron nitride. Okay, I always make it disappear. I don't know. So after the experiment, there was a considerable work performed by the group of Professor Wei Kang at the University of at the Peking University to develop a model to reproduce this data. And the first step of this model was indeed to calibrate this model with respect to the low pressure equation of state point which are existing, which are contained in the data bank, which is called RAS bank. And by changing the energy in the unit cell, it was possible to reproduce well this low pressure data and then compare the model which was developed to the new set of data. And indeed, not only the model was able to reproduce well our data with hexagonal boron nitride, not only it was able to reproduce well the data from Omega with cubic boron nitride, but it could also predict the different phases of hexagonal and cubic boron nitride, the melting curve, and the changes to the liquid state. And you see here we have the new phase diagram compared to the Hugonot curve, which is the state, the ensemble of the state that you can get by shock compression. And you see that indeed the Hugonot curve crosses this phase curve, crosses the melting curve at about 7,000 degree Kelvin, which is a factor of 2, almost a factor of 2 below the melting curve of diamond along the Hugonot curve, which means that indeed using this material as an ablator, you could really lower the foot of the laser irradiation and produce a implosion which is much more isentropic, which will reflect in the possibility of getting higher gain. Okay, we made many other experiments in other facilities, but I think that I will skip most of them. I just want to tell you that we use the different characteristics of the different lasers to exploit them to get more data. For instance, at the Pulse facility in Prague, because this facility allows to get higher laser intensity on target, we could get higher pressures. There was a problem, however, because in this case the laser pulse was quite short, which does not mean, it does not allow to get a constant shock pressure. The shock pressure is decaying in time because of the short pulse duration. So we had to make some correction to take into account this decay of the shock pressure in time. Another experiment was made at the LI facility, and in this case, the advantage of this facility is that this is a new laser system which allows to produce kilojoule laser energy with a repetition rate which is much higher than what you can normally do. I mean, facilities like Shenzhen 3 or Gecko can make a couple, 3-4 shots per day. Pulse can make maybe 10 shots per day, and here in principle you can make a shot every 3 minutes. And again, we were getting result. And in this case, of course, we know that direct drive is much more efficient than the indirect drive in creating shock pressure. So indeed, at the LI L-Force laser, we could get the same pressure, the same order of magnitude of the pressure as in Shenzhen 3P, with the energy which was 10 times less. On the other side, the quality of the data which was obtained in the Shenzhen 3P was a bit better, mainly thanks to the quality of the target and to the quality of the diagnostics. Well, I just want to say that in addition to studying hexagonal boron nitride, we were also making experiments at Gecko and also in Shenzhen 3P, but I do not have the data here now, on cubic boron nitride. In this case, the target concept was different. Instead of getting 2 steps, we were getting 2 layers, one after the other. So we were measuring the velocity in quartz and then the velocity in the cubic boron nitride. And here something has happened, so I don't know what is, but basically this was just the images from LISER and SOP. But we also had a additional diagnostic, which is quite interesting at Gecko, which is a SOP resolved in wavelength. So at each time we can get the the shape of the spectrum of the light emitted from the body. So here we see the emission from the quartz layer, and then the shock goes to the boron nitride, where there is a lot less emission. And we can, taking into account the sensitivity of the system, of course, we can interpolate this spectrum with the black body to try to get an information about the temperature reached by the material. And indeed, these are the data which we obtained at GECKO for the equation of state, the pressure versus the compression. And these are the data from the temperature. And this is very interesting because measuring the temperature is usually something which is not related to measuring just the thermodynamic parameters. You need an independent measurement, and this is usually much more difficult. And you see that for each shot, we had the two diagnostics because we were measuring this spectral SOP. So we were getting the temperature from the shade, but we were also getting the temperature from the normal SOP diagnostics, because of course the temperature, again, through black body radiation, is related to the total emission. And you see that the agreement between the two diagnostics was quite remarkable. And this is again compared to different models. And you see there are models which are based on simple models like FEOS or FPOS. And there is again the model of Wei Kang, which on this plot does not seem to be in better agreement with the data as compared to other models. But indeed, it is physically more sensitive, more reliable, because you see that there is a kind of plateau. This is the yellow curve. There is a kind of plateau at low pressure, which seems to follow the curve for the melting curve. And this is indeed what we expect for the Gonio curve, because, I mean, the temperature will not change until when the shock has transmitted to the material an energy which is equivalent to the latent heat of the transformation. And sorry. It's coming back. And these are our data for cubic boron nitride compared to the data from Omega and compared to the model developed at the Omega laser facility. A final point, we can also describe the decrease of temperature in time, because of course now we can follow the evolution of the spectra and the evolution of emissivity in our diagnostics after the time at which the shock goes from the reference material quartz to boron nitride. And we see, okay, these are just preliminary data which needs to be confirmed, but we see a decrease of the temperature in time as we expected. Here, the data of SOP and the data from the spectral streaked optical pyrometry, for the moment, do not seem to agree well with each other. But you see that indeed we are getting closer to the melting temperature of the material, which is of course what we want to see from the experimental point of view. So in the future, we also want to do something else. We want to try to make a double shock experiment, launching a first shock to get a small compression of the material, and the second shock to get a bigger compression. And this allows to get off Hugoniot states which are not laying on the Hugoniot curve of the material. And so, conclusion, well, we were getting high pressure data for HBN and also for cubic boron nitride, which are complementing the existing data at low pressure from the RAS bank, and at high pressure from the omega experiment. And the DFT-MD calculation developed by Weikang and collaborator are in very good agreement with available Hugonot data. Maybe we still have a problem with temperature, but we will address this problem. And the melting temperature boron nitride along the principal Hugonot in the calculation is almost a factor of 2 below the melting temperature of diamond, which opens interesting possibilities for inertial confinement fusion. So this is my talk. I just want to conclude by saying that there will be another workshop in Turkey in October. Let's say that this is the twin workshop of this one, but in Europe. And there will be a special issues on proton boron nuclear fusion for the journal High Power Laser Science and Engineering, with the guest editor of Katarzyna Batani, Pablo Cirrone, Ioannis Fitilis, Bing Liu, and Daniele Margarone. And of course, submission to these special issues are welcome from this workshop too. Thanks again.
Thank you, Dimitri. We have time for some questions, so the talk is now open for questions.
Michael.
Thank you for your interesting talk. Tell us, please, did you analyze the possibility and expedience of optimization of isotopic composition of boron? I mean the following. In principle, in some situations, it is desirable to increase the density of ablator in order to suppress growth of instabilities at the stage of strong compression. And second, so it is desirable to use heavy isotope of boron. And recently I have proposed such a trick with diamond ablators.
Yes.
And secondary, if you use indirect drive, it is desirable to provide equality of densities of doped layer intercepting X-rays and preventing preheating with density of undoped layers. So this can be achieved by means of optimization of isotopic composition. Briefly saying, it is possible to use relatively heavy mixture.
It makes the answer difficult.
No, actually, there is
This is one phrase.
there is a short answer and a longer answer. The short answer is no.
What is your
the longer answer is actually we didn't investigate the isotopic composition of the material. We were just using natural boron. But of course, it is very interesting to go to study boron 10 and boron 11.
And mixtures providing
Yes.
quality of density of
Yeah.
doped
And actually, concerning the other question which you made about the problem of preheating when you use all round, indeed, initially we were using targets which included plastic ablator, the gold layer, and aluminum base to stop the X-rays. But in the end, we switched to only using a much thicker aluminum layer, which could stop the X-rays anyway, and which did not provide all the problem of reflection of the shock at all these interfaces.
Thank you very much.
Other questions? We still have time for one or two questions. Martin?
Well, Dimitri, this is an excellent talk, much of which I have difficulty understanding. It's something I need to study. But
Yeah.
I have a very simple fundamental question. Heisenberg uncertainty principle says that if you compress your future target to close to ignition or something, close to pre-burn, the size of which is going to be very small, because right now the compression ratio is not very large. Okay. suppose you ended up getting it down to as little as, I don't know, a fraction of a millimeter, right? That size gives you an uncertainty range in the energy that you can determine contained in that little sphere, right? So what is that? In other words, this is much more an educational question for myself. I like to understand in the event that you achieve your goal to some degree, for people, and you have certain estimates about how much you need to compress. Under that condition, what is the uncertainty range in the energy content in that aspect?
Okay, I never asked myself this question. In a current experiment, at Livermore with DT, the final size of the target of the compressed fuel is indeed much less than 1 millimeter. You can say it can be of the order of 100 micron, but the hot spot is even much smaller than this. I need to do the calculation, but I suspect that this indetermination of energy related to Heisenberg principle is not so big with respect to, but again, this is a feeling and not an answer.
This is just what we want to do in this workshop, ask questions that have not been asked before. So thank you for the questions and thank you again.
But just I want to add something more. In this experiment, instead, we are not going to very high compression. As you saw, the compression is about a factor of 4, but this is because this is related to the physics of the ablator. So the ablator is compressed much less than the fuel because the compression of the fuel comes from the accumulation of the spherical compression in time.
Okay, Dimitri, thank you again. Now, our next talk is by Eric Lerner, and the topic is about decaborane in a plasma focus. So this is also a very interesting material that we have to look much more deeper into it. Eric, please. I give you a warning.
Right.
Thank you, Peter. Bottle of water. All right, well, thank you for that introduction, and thank you to all the organizers of this great conference, to Martin and Catherine and everybody. So today I'm going to be speaking about fusion experiments with decaborane in a dense plasma focus. And I want to first recognize my collaborators at LPP Fusion, Dr. Syed Hassan, Ivy Karamitsos, Rudy Fish, and our new research assistant, Sam Grun. So the goal of our work is to develop a compact 5 megawatt PB11 fusion generator to accomplish the same goal as Martin said, to deliver compact, cheap, safe, decentralized energy with no radioactive waste. So this is an artist's conception of approximately the size of a 5 megawatt unit. Now, we've been working with a dense plasma focus for a great number of years, and the DPF was actually invented back in the 60s, but I know many people are not familiar with it. So I just want to briefly say, how does it work?
And the basic principle is a little different than other fusion devices because we're trying to use the natural instabilities of the plasma rather than fighting these instabilities. So let's see whether we can get the no.
I see that I'm not the only one.
We need to get the video working. There should appear the scroll underneath that we saw. Yes. Okay. Yeah, you can press here. And now we have to get it back online.
Yeah.
Okay. So what happens is a pinch effect concentrates the current that's released by the capacitor bank, and a second effect kinks this up into a tiny plasmoid, which is self-contained by extremely powerful magnetic fields of the order up to thousands of Tesla. Based on that compression, there's viscous heating that generates temperatures relevant to PB11 fusion. So this is an extremely compact device, even compared with the spherical tokamak. The core of this device is electrodes. The anode is in the center and the cathode is around the outside, separated by the white ceramic insulator. So this is made out of beryllium, and the radius is, as you see, just a matter of centimeters. So this is a very small device in a very small vacuum chamber. So the vacuum chamber is only 2 meters tall, and the entire experimental room, including our 60 kilojoule capacitor bank, pretty much fits into the size of the vacuum chamber of this spherical tokamak that you just saw described. So we have similar peak currents right now, about 1.6 megamp, and a peak power during the microseconds that the machine is firing of about 60 gigawatts. Now, using deuterium, which we were using for a number of years, we have achieved some of the highest values in fusion research. As you can see, we've achieved and published in peer-reviewed journals 260 keV, which obviously is of interest for PB11. And the amount of energy we produced with deuterium is among the highest results relative to the input power, energy. So one of the great advantages of the DPF is it can produce high densities without the inefficiency that is inevitable in laser compression. So like in other magnetic confinement, we're using electricity from the start so we can get a lot of the energy into the plasmoid. And this makes all of our operations fairly cheap and efficient. The project to date has only spent $12 million. So what I'm going to present today is the initial results that we have obtained with decaborane, some of the problems and some of the solutions over the last year to advance to our next stage, and what those next steps are going to be. So we started our experiments with decaborane starting in November of 24. Now, decaborane is a solid at room temperature, so we have to heat it to modest temperatures to generate the vapor pressure needed to run our machine. The limiting problem is we use mylar as a key insulator. And Mylar really starts to get brittle if you bring it much above 100 C. So the problem is to have nothing in the chamber below 75 C and nothing above 100 C, which is actually harder than we thought. So by June of 25, June of last year, we had achieved comprehensive insulation, better thermostat control, and heated gauges to allow us to get the conditions to start firing with decaborane. And by the way, right now we're using natural decaborane, but we have obtained 99.99% PB11 for future experiments to avoid radioactive products of the B10 reactions. So the first problem we encountered was, and this was a quite serious problem, was that the hydrogen and the boron that are released from decaborane separate during that rundown phase that you saw at the beginning of the animation. And the reason for this is quite clear. The reason is that the boron ions encounter the alphane critical velocity. Now, this is not the alphane velocity, but the alphane critical velocity is when the kinetic energy of an ion moving into a motionless plasma reaches the ionization energy of a given state. At that point, energy is flows into ionizing that state, and you can't exceed that velocity until all of that state is ionized. So what happened is we had the boron encounters a speed limit of 6.7 centimeters per microsecond. The deuterium or hydrogen that it's mixed with does not encounter that speed limit because, of course, it's already totally ionized. And therefore, there's a separation which prevents fusion reactions. So we had plenty of evidence for this. First of all, we saw the traces of the current and voltage deviating at the places we expected them to on the basis of this hypothesis. And we saw that the boron was depositing on the beryllium electrode, forming beryllium boride compounds in a structured manner. And I don't know whether you can see that our very well ordered grooves and ridges that are produced by this process, which is analogous to hydrodynamic erosion, which produces these nice grooves and rocks around all continents. Except the difference is the current has to get through this insulating layer to reach the anode. So this basically starts to channel the current into smaller and smaller dimensions, which unfortunately led to a crack in our anode. And this terminated after only 2 months our experiments in August of last year, just a year ago. So that was problem number one. But nature was kind, and the last shot, not coincidentally, showed the first pinch in pure decaborane. Now, the pinch is what occurs when that little plasmoid forms. The denser the plasmoid, the greater the pinch. Now, the first indication of the pinch is this little peak in the trace of the high voltage probe. So this is a peak of only a few kilovolts. And this shows that it was a pinch, but a very small pinch. This is an example of a big pinch. This is from the record yield that we obtained in June of last year with deuterium. And you see the spike, in this case, a double spike, goes up to tens of kilovolts. So that's what we want to see in a big pinch. We got quite a small pinch. The fact that the peak of the current occurred back here at 1.57 microseconds. I don't know why the creep disappeared. And the pinch occurred over at 2.12 microseconds. That was a clear indication of the separation of the hydrogen and the boron, with the hydrogen arriving at the end of the electrode early and the boron arriving late and creating the pinch. Now, the fact that we got a pinch, even a little one, was confirmed by the spectrum. So the blue line was shot the same day with no pinch, and the red line is with a pinch. And you see the growth of the boron lines greatly increased during the pinch. The whole pinch is hotter than the non-pinch, and there's an especially significant increase in the boron-4, the triply ionized boron, showing again that the boron entered into the hot part of the plasma. And by the way, when we're talking about the plasmoid, we're talking about a very small area, which in a medium pinch is 250 microns in radius. The pinches that we desire, the plasmoid would only be about 10 to 15 microns in radius. And finally, the last shot, this pinch shot, also showed first evidence of filamentation with near pure decaborane. So in the animation, you saw the first stage of compression is filamentation through the pinch effect, but that only can occur if there is a correct breakdown of the gas. And for the first time in that final shot, we saw that filamentation in pure decaborane. So that was problem number one. Problem number two we encountered when we started to disassemble the machine, and we saw that the insulator was not very clean. So the exposed part of the insulator is coated with a discontinuous coating of beryllium. That's okay, and that's desirable. That keeps the current close to the insulator and forms a sheath vulnerable to filamentation. But these dark deposits, which were below the plasma level, were not desirable. And we determined very quickly, because we'd seen them before, that this was siloxane, which was being emitted from the silicone gaskets that seal the device next to the insulator. So that clearly had occurred because of insufficient bakeout of these gaskets. And we looked back on our data, and we hadn't been paying attention to it, but when we looked back on the data, we saw a giveaway, which was the silicon line at approximately 704 to 707 nanometers. And that was quite strong in many shots, including our last pinch shot. So the problem was we had to get rid of this silicon contamination. Problem three, again, emerged when we looked back at our data. We are using, as part of this DPF, an axial field coil, which produces a small initial axial magnetic field, which induces a spin in the plasma. Controlling that spin is vital to controlling the formation of this spinning plasmoid. Too much spin and the centrifugal energy resists compression. Too little, and you don't get the kinking that forms the plasmoid in the first place. Now, what we found was that the axial field coil, which only has a small DC current, was developing through interaction with the plasma very big oscillations. And these oscillations were hundreds of amps, much bigger than the imposed current. So we needed to get rid of those. So in the past year, we've been working on solutions. So we started again in June after we replaced the anode with a new anode to address these problems. Now, we did a better bake out and we thought we would get rid of the silicone. But when we started firing the machine with cleaning shots just 2 months ago in June, we found out no, there was still a heavy coating of siloxane. And we were quite frustrated in the first few weeks. We were making pretty little progress with removing this with cleaning shots. So what you see here is these colored deposits. The natural color of beryllium is just gray. And you have these colored siloxane deposits in June. And when we started firing our cleaning shots, initially the siloxane just moved around, and then it started to be converted into silicon dioxide, which is a whitish, very tough ceramic. So that wasn't very good. And we weren't making any progress at all in removing this this silicon dioxide line, which is over there at 700. Maybe this one. Okay, thank you. So that was a problem. So this is the silicon line, and you can see it wasn't going away at all. So Sam did a AI-assisted literature search and came up with the idea that we should cause the anode to vibrate, because silicon dioxide, while very tough, is very brittle. So we would just shake it off. So we knew a good way of getting the anode to vibrate, which was generating the pinch with pure deuterium, because the pinch heats the inside of the anode rather violently and causes, well after the shot, a vibration. So sure enough, this suggestion worked. And just about a week ago, in the course of 4 days, assisted by my colleague Ivy Karamitsos, we brought the silicon line down by a factor of 20. And you see this is the before with this red line, and the after, I doubt whether you can see this very tiny residual line, 20-fold reduction, which was pretty much what we were aiming for. Less dramatic, okay. Less dramatic was the removal of this layer, but you can actually see this layer is almost continuous white here, and now it's broken up into little islands of remaining silicon dioxide. So that problem seemed solved. In the course of these shots, we were playing with the filter circuit to reduce these oscillations, and again, we got good success. The oscillations now, instead of hundreds of amps, are approximately 1 amp. So we again got 100-fold reduction in the oscillations of the field coil. Now, the basic way we knew to prevent the separation of the hydrogen and boron was to prevent the sheath from exceeding the speed, this alphane critical velocity speed limit. And that's by putting more decaborane in. To do that, we had to heat it more to generate more pressure. And just last week, we achieved a test fill to 2.1 torr, which is close to our goal of 3 torr, which we expect to achieve next month. So that's sufficient to achieve the correct peak velocity. In addition, we plan in the next experiments to increase the level of pre-ionization, a gentle current that pre-ionizes the gas and leads to a smoother breakdown and a more symmetric compression. So, of course, I had wanted to present the results of solving these problems, but as you can see from the dates, we ran out of time. So these experiments will be done in August. And the first goal of these experiments with these improvements is to obtain measurable fusion yield from decaborane. We expect we can measure a yield of as low as half a joule indirectly by the secondary reaction of alpha particles with boron. So that produces neutrons, which we can measure externally to the vacuum chamber. Our second goal during the course of the summer and fall is to optimize the parameters to achieve a much greater, but theoretically possible yield of 100 joules of PB11 fusion energy. And the final goal, which we're also aiming for in this calendar year, is to upgrade our device from 8 capacitors to 12 capacitors, increasing to 2.4 megaamps. At that level, we expect that it will be theoretically possible to achieve net energy out of the device, more than energy than we put in from the capacitor bank. So these are our ambitious goals, and I thank LPP Fusion's funders, Able Foundation, and our many investors and donors, and again to the symposium organizers. And thank you for your attention.
Thank you, Eric. So the session is now open for some discussions. We have still a little time immediately.
Sorry, naive question from a person who is not specialist in the field. So, why do you use solid decaborane instead of starting with the gas? And second, for proton boron fusion, usually we say that we need much more hydrogen than boron to reduce the Westerstrom losses. And again, this decaborane does not seem to fit this picture.
Okay, to be clear, the decaborane starts out as a solid because that's its state. It's a powder at room temperature. We put the decaborane into a sample chamber, which is heated to produce the vapor. The vapor is what fills the chamber. So the chamber has vapor in it. But the trick is, if you don't heat the chamber evenly, the gas can change its state back to the solid and deposit. So we're running with decaborane vapor. We start with the solid just because that's how nature gives it to us at room temperature. Now, there are other boranes that are gases at room temperature. There are two reasons we don't use them. The biggest is safety. All of the boranes are toxic. They're not terribly toxic, but they are toxic. Decaborane is a solid at room temperature, which means that at all points, vapor is under negative pressure. Vapor is much lower pressure than atmosphere. So there's no danger of it escaping. With the lower boranes, you start with the gas and you do have, a potential for an accident. So that's one reason. The other reason is we don't think we need lots of hydrogen to suppress bremsstrahlung because, and this was a turning point in our research, we realized back in 2005 that that there's an effect that's very relevant to dense decaborane. And this effect we call the quantum magnetic field effect. And this is a quantum effect in which if the magnetic field is strong enough, it becomes impossible for the slower moving ions to bounce the electrons into the next quantum state. And therefore, the transfer of energy from the ions to the electrons becomes much slower than the transfer of energies from the electrons to the ions. So you can develop a huge 25-fold difference in ion temperature versus electron temperature, and that suppresses the bremsstrahlung. That's what we're aiming for.
Thank you. Another question? I don't see this at the moment, so Eric, we thank you. And so on the next meeting in Istanbul, you had maybe some better results because you said August and we are meeting in October. So
Perhaps. I don't know whether we'll be able to make it to Istanbul.
Thank you again.
Thank you very much.
And now we have coffee break and the group.
A group photo. So please everyone go to the first block first for the group photo and then have your coffee break. The break will end at 10:50. 10:50. Please come here on time for the next session. Thank you.
is online. So we have already organized the connection and tried out everything about his talk. So we can start promptly at the appointed time. So good. 1 minute and counting. No, still. Okay, thank you very much. Since everyone is here and our speaker is ready, why don't we start? 李老师。
好的。
Okay, we have two speakers this session. The first speaker is by Professor Li Zihuan, and he's going to talk about triple coincidence analysis of the P-boron11 to 3-alpha reaction from Beijing University. Thank you. 请开始.
Okay, so good morning. So first, I would like to thank you, the organizer, to give me this opportunity to present our recent work. And sorry, I will stop. Stop video. Okay, so the aim of this talk is to reconstruct the complete 3-alpha events and use them for the more robust reaction cross-section measurement. So this is contents of my talk. So I will first introduce the relevant carbon-12 states and decay channels, and then discuss about historical single alpha cross-section and so its model dependence, and then so I will discuss about the complete 3-alpha constraints of decay amplitude, and later I will introduce our detector response study for complete events counting, and finally I will give a summary. Okay, so let me begin with carbon-12 states populated through the entrance channel. So this is a reaction entrance channel of proton and the boron11 ground state is known, and so the state carbon-12 state populated in this reaction is determined by the orbital angular momentum of the proton. So if this proton come with S waves, then so it populate 1 minus and 2 minus of the carbon-12 states, and if it's from the P wave, then it can populate 0 plus to 3 plus state. So this figure I summarize the possible resonance state above the proton and the boron threshold. And so then we can see that there are several peaks with different characteristics. Some is very narrow, some is very broad, and some area is uncertain. And so here are some equation how to convert the proton energy to the excitation energy of the carbon-12. So once we use the certain energy for the proton energy, then we populate a certain excitation energy. So this reaction is this population is controlled by the proton energy. Okay, so then the next question is that how this excited state proceed. There's in the reaction mechanism there are two possible ways. One is the so-called direct 3-alpha breakup, means that this excited state directly emit 3 alphas and go to the final state, and the other way is that it could pass through the beryllium-8 intermediate state and then proceed to the 3-alpha states. There are some measurements. There are some measurements that Beaker done at 1982. They examined this through some coincidence measurement. So they conclude that the sequential decay for this reaction is dominant through the beryllium-8, and no significant phase space-like direct 3-alpha contribution has been seen. So then, this then in this energy region, so proton energy is less than 3 or 4 MeV. So sequential dominant is established. Then so we could ask the next question. So how does detail the three body dynamics proceed? So here is sequential decaying picture. So here are some terminology. So for this kind of reaction, carbon-12 first emit alpha. So this alpha we call it as a primary alpha. Then so it populates beryllium-8 resonance state. It's immediately decay to the two alphas. We call these alphas as secondary alphas. And there are two decay channels. So one is this excited state pass through ground state. This ground state, so resonance state is very narrow. So width is around 92 kV. So then it's emits secondary alphas. The other, so this decay channel we call it as a alpha 0 channel, and the other channel, so the primary alpha proceed to the beryllium-8 2+ state. This 2+ state is a very broad resonance state, and then emit secondary alphas. From the angular momentum and the periodic conservation, we can somehow assign the possible angular momentum, so primary alpha carries. So here, I just want to emphasize one state. For example, this 16.62 MeV 2- state. This decay is forbidden for alpha 0 channel, but it's allowed for the alpha 1 channel with the angular momentum could be 1 or 3. Then let's look at the experimental signature for the alpha 0 and the alpha 1. So alpha, as I mentioned before, so alpha 0 pass through very narrow beryllium-8 ground state. So in this case, so alpha 0 and the beryllium-8 is some kind of two-body kinematics. So this alpha 0 energy is fixed for the given proton energy or excitation energy. Then so if we look at the single alpha spectrum, so alpha 0, we can see very distinct alpha 0 energy. Alpha 0 peaks appeared in the high energy end. So then we just simply count peak area. Then we can obtain the alpha 0 channel yield. And for alpha 1 is much complicated. So because it's passed through the very broad beryllium-8 2+ state, then so its distribution is very broad. But unfortunately, it's also overlapped with secondary alphas. So comes from alpha 0 channel or alpha 1 channel is make some continuous background. So if we try to extract this alpha 1, then we should rely on model. So different model gives a different ratio and a different shape. So once we obtain the alpha 0 and alpha 1, then we can know how many reactions are achieved. Then we can calculate the reaction yield. Okay, so next section, I will go through several historical study for this cross-section measurement. So this here is that work done by Beaker and his collaborators. So they use the two different beam and the target. The first one is that traditional proton beam hit the beryllium target, and the second one is that inverse kinematics. Boron. Okay. So boron beam hit the hydrogen target. So the energy at the center of mass system is around this area, and they use several detectors at different angles to measure the single alpha spectrum and they use several two detector coincidence to check the reaction mechanism. And here is the typical single alpha spectrum, and so this curve is fitted by their model. We can see here that so their calculation or their models so reproduce the main feature of the so this experimental structure, but some area, for example, at the so 16.11 MeV. So they tried several several angular momentum, but all fails. And the other one is that so important 16.62 MeV. So they use the so pure L1, so angular momentum equal to 1. But so later it's changed to so different work modified this kind of this assumption, this assignment. Okay, so here is that so how here I show how the so cross section is obtained from the so finite angle measurement. Finite angle measurement. So here this point is that so several angle measurement. Then we fitted this trend with this kind of formula, standard formula. Then integrate this angular momentum over 4 pi. Then so we know how many alpha 1 is in the so in the 4 pi. And so also same for so alpha 0. So this is the so how so cross section is obtained, and so this is the another so experiment. This experiment is designed to examine some representative state to investigate the so decay mechanism. So this experiment also used several so finite angle measurement, and here they developed the so sequential model. This model I will mention later again. So they use their model to fit this alpha 1 so broader energy area, and so L1 this is so fitted by L1 and fitted by L3. So from here, so L3, so this fitting is much better than L1. So finally, they conclude that so L3 is the so angular momentum of the so primary alpha. So as mentioned before, so Beaker assigned the L1, and so they also examined another state. So here, so this figure show us that so this kind of alpha 1 extraction is very sensitive to the model assumption. Then later, so the other experiment is done by Asperger and his collaborators. They did a similar experiment, and then they used a different strategy. So in his experiment, they, so this is a so single alpha spectrum. Single alpha spectrum, but because as I mentioned that this is alpha 1 extraction is strongly model dependent. So they reported experimental data with this kind of strategy. They put so 2.75 MeV window here, and they report so all alpha count within this window. So this is called as an alpha exp, and the W means the window. Then so Sikora and Weller so use the model to reconstruct the so whole so alpha cross section. So here is a strategy they use. They first extract the in Windows alpha 1 counts using model predicted so alpha fraction. So by using model, they can they can calculate so how many alpha 1 is in this window. This calculate this ratio. This ratio multiplied by so data from Spriker. And then so it's by multiplying this factor. This factor is that so total alpha counts to calculate the total and the window ratio to extract the whole energy range of the alpha 1 counts. So in this model, they also use the so many assumptions. This is the main assumption. They simply use so 2 minus and L equals 3 for the proton energy below 2 MeV, and 3 minus and L equals 3 for the proton energy larger than 2 MeV. Okay, so here is that so collected experimental data for the different literature. So this is for alpha 1 and alpha 0. There is you may notice that there is a much different so scale. So alpha 0, so maximum is 60 millibar, but so alpha 1 is at 1,600. So in general, alpha 1 is dominant, but we can see that so historically different measurement is not matched each other. And so this is the total cross section is sum up this alpha 0 and alpha 1. So historically, there are so two important evaluation. One is based on Beaker's data, and the other one is from the Spraker's data. So this is much different. So I want to summarize the so existing cross section, comments on the existing. So historical cross section is derived mainly from multiplicity 1 single alpha spectrum with limited coincidence constraints. And the broad alpha yields depends strongly on the decay model, but it's not tested very well. And also importantly, so many many details not considered in this model. So it should be solved at the next studies. So before I switch to the complete 3 alpha measurements, so here I want to introduce the so-called complete sequential R matrix framework. This framework will be used to the next step analysis. So I don't want to go to the details of this formula, but importantly, there are some 3 important features. One is that so broad intermediate state line shape is described here, and and also in this model, so coherent, so possible angular momentum mixture can be introduced, and also the other. Oh, okay. Oh, okay, 10 minutes. Okay, I should go quickly. So this is both symmetrization. This is very important. I will mention later. So then, so to examine 3 completed 3 alpha dynamics, people usually use the Dulles plot. So Dulles plot use the complete 3 alpha events, and one events so it's so corresponding to the 1 point in this plot. On this plot here, I give one example. So here is the 3 body measurement for the 16.11 MeV. They use the so high segmented detection array, and this is experimental Dulles plot, and so this is a model calculation. They use the 4 models. So M1 is the direct 3 alpha so breakup, and so M2 is that so sequential with L equal 2, but so both symmetrization is not considered, and this is with symmetrization, but with different angular momentum. So just by quick comparison, we can see that this figure is matched with the M4 so assumption. So Dulles plot give us a very very good comparison between data and the model. This is another experiment. So another experiment. So here they considered so full so R matrix framework. Then it's give the different result for the this state. So it's different from the so assignment from the state. Okay, so I want to spend a few minutes to emphasize our work. So our work is so try to have the model independent cerebral cross-section measurement. Cerebral cross-section measurement. So as mentioned before, so this extraction strongly depends on cross-section strongly depends on the model assumption. So if we have idea is very simple. If we have idea of full coverage, then we can count all three alphas. Then we just from this number we just divide by 3. Then we can get experimental cross-section do not need to rely on any decay model. But so we know that this kind of full coverage is impossible for our real situation. So we did several different similar approach, but we choose several high coverage silicon geometries, and we compare with different model, different state, and then we try to see that even state and state and this model change, but this efficiencies 3 alpha efficiencies does not change. That's so our goal. So here we use the several representative states, cover the different angular moment, different spin and different parity. Different parity is located here, these two and this one. And we use the different detector setup. This is an existing setup mentioned before, and this is called a Z0 setup. This is a G1. We put another two W1 make a very close close geometry, and the other is we add this kind of detector setup at the forward angle to cover small angles. So here is the simulation. Simulation was done by different configurations. This is the state we studied, and we use the pure phase space, pure L0, L2, and coherent is a mixture of those two. This is for the 4 pi coverage, and this is a G0, G1, G3 different setup. So from here to here, we can see distinct different because G1 only cover very limited 4 pi. So G1 we put another W1, then you can see it's recovered a lot and almost identical for the full setup, and the G2 is also similar. So this is a different state studies, and then finally, we studied first we examined the absolute M3 efficiency. M3 we defined several different efficiencies. This is so-called model efficiencies. It's a simulated reaction number, and this is reconstructed threefold events, and the state means that we examine with different assumption, and we averaged, and the setup means that we average all state and all models. So here is that from the different setup we can see for different state. So we can see that from G0 from G0 to G1 we can see that three alpha efficiency is increased a lot. So here G0 is 8%, but that is 20%, and the G2 changes minimum. So from this point of view, G1 cover large coverage give us better efficiency. But if we want to achieve that model insensitive, it means that this efficiency should not change with different models. So we check it with efficiency spread. Efficiency spread is defined here. So we pick up a maximum and minimum difference and divide by the average efficiency. So if we set up, if this spread is smaller and smaller, then we can say that this setup is a model independent. So disregarding we choose different models, but it gives very identical efficiencies. So that is listed here. So basically we should see this these curves. For the G1, we choose different state and the different model assumption. It gives a spread, a relative spread as a 16 point. And for the G1, we add two additional W1, then it's decreased to around 6%. And so we add a forward angle. It's a little increase, but it's similar. So then we can conclude that G1 gives the smallest setup spread, and the G2 we don't see much change, so that the G1 gives a better efficiency and stability balance. Balance is here, so we investigate the merit for the forward angle coverage. So we put the G2, we put the forward angle coverage, then efficiency. So three body events efficiency is increased towards a smaller angle. So that's as seen here. That doesn't help much for the this efficiency and the spread, but it's important to constrain the forward angle distribution, angular distribution. Okay, so here is the summary. So I review the historical single alpha 1 cross-section measurement, and so emphasize that the complete 3 alpha measurement is very important to achieve the correct alpha 1 cross-section. And so we studied a different detector setup, detector response, and the G1 setup gives set up a mean efficiency about 20%, and overall state model spread is around 6%. This is I think it's a very good result, but we need to examine this at real data, and so for the next step, so we are developing resonance mixing models. So maybe you may notice that before we just discussed some certain state, but between these two these two strong resonance, and in the middle of this strong resonance there should be resonance mixing. That's not been discussed yet, but we are developing resonance mixing model, and so we needed to test more broader decay models. And so the other I want to mention is that we have we have the data for the G0 experiment data, and so 3-body analysis is underway. Okay, thank you so much. That's all.
We're over time, so maybe it's one most important question, if there is one. Questions? It was an excellent talk. It's very comprehensive, but we ran out of time.
Okay, sorry.
No problem. So our next speaker.
Thank you so much.
Yeah, thank you very much. Our next speaker is Mikhail L. Shmatov from Yoffe Institute, and he is going to talk about ball lightning, its radiation hazards and importance for fusion studies. Please open up your mind. Thank you. Please.
Ball lightning is a light emitting object with lifetime from about 1 second up to a few minutes, which sometimes arises due to electrical activity of atmosphere. And I will demonstrate that the fact of existence of such objects is very interesting and important for plasma physics in general, for fusion studies, for aviation safety, and even for everyday life. although the probability of to meet ball lightning is relatively low. For example, for Russia and the United States, it is assumed that the probability to meet ball lightning during the life is about 5%. The opinions about some properties of ball lightning are contradictory, and first of all, there are different opinions about the ability of ball lightning to cause radiation sickness. The assumption about radiation hazard of ball lightning appeared about 60 years ago, and this assumption is based on both observational data, and this is especially important, and several ball lightning models. Here I presented lists of some works. Please note that Carpenter has written this in his PhD dissertation more than 60 years ago. The first report corresponding to assumption about the very high radiation hazard of some ball lightning was published many years ago, but the years of publication here demonstrate that the probability of falsification of this report is excluded, because at that time information about radiation hazard was not available. A fragment of this report is reproduced here. I'd like to note that the author who worked in the US consulate in Maracaibo mentioned violent vomiting, virulent raw sores, and loss of hair. This is very similar to strong influence of ionizing radiation. In particular, vomiting can start during the time of about 5 to 20 minutes after the radiation with a dose of 6 grays, or in other terms, 600 rads. I would like to say immediately that the probability of surviving after receiving such a dose is very low, but in principle, surviving is possible. And Garfield was probably the first who interpreted 90 years later the report about this accident as about accident associated with ball lightning. I will present my model, which use no exotic assumptions, and explain in particular this report. I must to say that opinions about ability of ball lightning, or more exactly of some ball lightning, to cause radiation sickness are contradictory. And for example, Stakhanov, who was a well-known Soviet researcher of ball lightning, considered such reports as a myth, although he received such at least one such report directly. But I repeat that he considered that this is not correct. I support, as already told, I support this assumption. In principle, it is necessary to take into account the following. Ionizing radiation can cause misoperation of brain. In some situations, ionizing radiation causes so-called X-ray hangover. This effect is similar to the influence of alcohol. Also frightening dreams, high-order cognitive impairment, and progressive dementia. And it is evident if after the influence of ball lightning somebody told some strange things, this can be, and the fact of dementia is more or less evident. This can result in unserious reaction on his or her word, but in reality, this can correspond to irradiation of this person, in particular his brain, by ionizing radiation. And unserious attitude, of course, can delay or prevent treatment. Proper for treatment of effects of ionizing radiation. And this the assumption that ball lightning emits strong ionizing radiation is very important for radiation safety, because in the worst case, biological effect can cause loss of ability of pilot to control the plane or helicopter. And more complicated effect is that ionizing radiation can cause operation of electronic or electric equipment due to short circuit in some devices. And the reports, according to ball lightning, sometimes turn on or turn off electric equipment are known for many years. Here I have cited a very good book written by Brandt more than 100 years ago. Kugelblitz is a German term corresponding to ball lightning. I will present my model, and the assumption of my model is written here. Ball lightning has a core consisting of cloud of electrons and almost totally ionized ions, which oscillate with respect to each other and undergo the random motion disturbing the oscillation. In especially interesting situations, when lifetime is relatively long and energy density of ball lightning is relatively high, the main losses of energy are associated with emission of Bremsstrahlung radiation. The ball lightning core corresponding to my model has some similarity to plasma clouds which arises in some other situation, and in particular I have proposed my model after reading some paper on direct drive laser fusion. In such experiments oscillating irradiation of a target can cause acceleration of large number electrons to high energies. These electrons will escape from plasma cloud, but the plasma cloud will acquire positive charge. This charge will attract the electrons back, and as a result, they will oscillate and preheat the target. And briefly saying, with this bad effect because it complicates fuel compression of the fuel. Also, very similar plasma clouds arises in so-called traps with electrostatic confinement of plasma. This approach is also called sometimes grid confinement, and such traps are known for several tens of years. And sometimes they can serve as an effective source of neutrons. But so I'd like to attract your attention again to the fact that plasma cloud with oscillation of electrons are well known. Also, they arise in some other situations, but now I will not say about all of them. According to my model, stability of ball lightning core is provided by the effect of oscillation itself and the atmospheric pressure. The role of atmospheric pressure is rather complicated. It compensates for the outward force arising mainly due to the three-dimensional geometry of the oscillation and random motion of electrons and ions. The situation with random motion is evident with something similar to usual pressure. As for three-dimensional geometry, I will present explanation slightly later. The core is isolated from the atmosphere by the depleted layer. Structure corresponding to my words is shown here. And according to the model, ball lightning arises due to formation of a converging flux of so-called runaway electrons. In the nature, the initial acceleration of these electrons occur due to the attraction to the positive charge injection into the atmosphere, for example, by ordinary lightning, by some other situation when this charge is effective, is sufficiently strong to create a ball lightning or cause some other effect, but is not sufficient to create observable lightning, and thunder, sound of thunder are also possible. The convergent fluxes of runaway electrons can be generated only due to so-called cold runaway, also called thermal runaway. This effect is the following. Here the effective frictional force at standard temperature and pressure is shown. How to use pointer?
反正红点啊。
Oh, simply this. The situation is the following. If the usual runaway was predicted by Wilson about again 100 years ago, idea is the following. If we have electron with some kinetic energy influenced by electric field, so if the force from electric field is stronger than the effective frictional force, electron will be accelerated if the electric field is stronger. But in the simplest situation, electron must be sufficiently fast. Here, the energy the field corresponding to breakdown of electron is about at such level, 30 electron volts per centimeter. And if electron has such energy, it can be accelerated by a field which is not sufficient for breakdown of the air. But if the field is very strong, about 10 times greater than a field necessary for breakdown, any electron will acquire very high energy. Of course, such a field cannot exist for a long time. The air will undergo breakdown, but I have shown that a strong acceleration of electrons is possible during the time of development of breakdown. So if we create a sufficiently strong electric field during a short time, I would say this time will be terminated by development of discharge itself. We can accelerate electrons to very high energies. And the initial acceleration of electrons seems to excite many modes of oscillation of electrons, but the losses of energy will quickly attenuate non-spherical modes due to emission of radio waves. And usually ball lightning has spherical shape, and therefore it is called ball lightning, because usually it has a form of the ball. And the energy lost by one electron, according to my model, can be described by some equation of such kind. This parameter is so-called radiative stopping, determined by cross-section flow interaction and energy emitted of emitted photon. The typical time of the loss of energy of ball lightning core due to Bragg-Strauss can be written in following. This is the maximum kinetic energy corresponding to the first oscillation period. So with this total relativistic energy, with the rest mass, and with difference is the kinetic energy. And we can divide the total energy on the rate of losses of energy during the first period of oscillation. And some complicated equation yields that in one dimension of model oscillation and in the Born approximation, typical time of losses of energy can be presented as a ratio of some function which depends only on the gamma factor of electron corresponding to the first period of oscillation. This parameter is average squared atomic number of component of air, and the key moment is the density of ions. My model contradicts to idea published many years ago by Kapitsa. Kapitsa has written that ball lightning cannot have some internal source of cannot exist due to accumulation of energy, because the losses of energy will be proportional to the squared radius, or in other words, to emitting surface. And the total energy is a product of volume density on the volume. He used scaling and the time of existence of plasma cloud created by nuclear explosion, when obtained with the sizes of several centimeter or several 10 centimeter correspond to very short time. But this is not applicable to the problem of ball lightning, because according to my model and in principle some other model, ball lightning is optically thin. Ball lightning therefore emits the energy from the whole volume and accumulate energy also in the whole volume. And the ratio of energy to the rate of losses of energy does not depend on size, at least in the first approximation. So, if we choose sufficiently low energy of ions, we can explain any time of existence of ball light. Formally, we could explain the time of its existence during or typical time of losses of energy with this comparable value, I mean times. For example, during 1 year. But this will be mistaken because we must explain not only the time of existence of ball lightning, but also, for example, its energy density corresponding to the values up to several kilojoules per cubic centimeter, or even a few tenths of kilojoules per cubic centimeter, which correspond to some reports. And also, for example, the amplitude of oscillation of electrons should not be too large. If we obtain that everything is okay, lifetime is about 10 seconds, the volume density of energy is correct, but the amplitude of oscillation is about 1 kilometer, this would be evidently wrong. So we can explain any time by means of choice of sufficiently low density of ions and as a result of electrons, because the density of electrons is about 7 times greater than that of ions. Ball lightning has, according to my model, some positive charge, and this charge is very important, but this absolute value of this charge is much less than the total charge of all ions. Yes, okay. So, density of electrons is proportional to the density of ions. Here I simply for illustration demonstrate equation using when calculating radiation for losses. I already told what should be explained from the viewpoint of energy requirement. And it is very important that the energy of ball lightning can exceed the value 0.15 joule per cubic centimeter, which correspond to the kinetic to the volume density of kinetic energy of motion of molecules of air. Sometimes it is declared that virial theorem prevents the ability to provide higher densities of energy. This is mistaken. Details were explained in two my papers. Usually the initial value of kinetic energy is of the order from 110 kiloelectron volts to 10 mega electron volts. These values seem to be very large, but everything is okay. When the initial value of kinetic energy, amplitude kinetic energy of oscillating electrons is about 50 kiloelectron volts and greater, final value of this energy is about 10 kiloelectron volts. So I repeat that the total ball lightning lifetime is several times, up to 10 times greater than the typical time introduced earlier, but they are comparable. Recombination does recombination at the sufficiently high electron energy. Recombination is not important. Now I will not present the details. I will answer if the problem arises. So this I have mentioned some pressure arising due to three-dimensional nature of motion. This is described by this parameter. Now I will not present some details. I can answer if the problem arises. Very important that ball lightning corresponding to my model must emit X-rays and gamma rays. And gamma rays, in principle, can be detected. And this is very good for me. It is very good for me that currently the search for gamma ray related to electrical activity of atmosphere is very popular. For example, Chilingarian and his colleagues has detected several fluxes of gamma rays, which were accompanied by this observation was accompanied by registration of visible light. I have presented some analysis according to which This data can be explained as observation of both visible light and gamma rays from a group of ball lightning. And now I'd like to attract attention to the fact that some parameters was chosen. And for example, initial amplitude of oscillation of electrons should be about 4 millimeter. This corresponds to the fact that it is not of about 1 kilometer mentioned earlier as an evidently mistaken result, or even 1 meter would be too large. Value radius of ball lightning cannot be established because location of source was not established, but according to the model, it should be in such range, for example, from 7 centimeter to 23 centimeter, corresponding to observational data. But the origin of light detected by Chilingarian et al. Was not established. In principle, this could be associated with so-called Sandalmo fire. Something similar was observed in Japan, and recently a very interesting observation was performed from airplane and reported by Marisaldi et al. Probably it is possible that Marisaldi et al. Recently detected radiation from about 500 ball lightning from the airplane in 10 flights. I will present the details if the question arises. Also, I'd like to say that my model explains very interesting results. Dmitriev has taken 4 samples of air influenced by ball lightning. He has unique equipment. The reason of the possibility of such experiments, or in other words, of presence of this equipment is not known, but in any case, he obtained the density of nitrogen oxide in air near ball lightning, and my model has explained this fact. And as for importance of ball lightning for fusion studies, I think that problem is mainly political. Presumably, the first statement of such a kind, as long as we do not really know what a Kugelblitz is, it holds out the hope that there is such a thing as a stable plasma configuration. This statement is very old. Also, the absence of reliable explanation of widely known natural phenomenon, the feature of which are evidently determined by plasma effects, can be used as an argument against the statement about the ability of plasma physics community to solve in observable future the problem of controlled thermonuclear fusion. So there is a hope that ball lightning is associated with some plasma configuration which can be useful for magnetic confinement fusion. But to the best of my knowledge, these hopes were never supported by realistic estimates. For example, the best paper is that by Roth, but briefly saying, he presented, for example, these arguments. I will not read it. But when describing ball lightning quantitatively, he did not took into account the pressure associated with magnetic field. He discussed the possibility of atmospheric of balance between atmospheric pressure and motion of particle, but he did not analyze huge magnetic pressure, formally huge, corresponding to the high volume density of energy. So I reproduce, but he has written one more interesting phrase, meaning that initially it is possible in principle to create ball lightning and later to try to obtain some useful information about its structure and in principle for fusion studies. I partly agree. Creation with him, creation of ball lightning in laboratory or in the field experiments with the use of ordinary or rocket triggered lightning will be very useful and probably will improve any model. The problem is how to organize these experiments. I consider that some scenarios corresponding to observational data, but some of the expected results of establishing the nature of ball lightning is the following. First of all, optimization of treatment of humans influenced by ball lightning, establishing the real danger of ball lightning for aviation and some space mission. In principle, it is known that there is electrical activity of atmosphere of some other planet, for example, Jupiter, and it is evident that elimination of some Jovian emission by lightning or ordinary lightning will result in large financial losses. And of course, solution of the political and technical problem related to fusion studies. So conclusion, the published information about several effects allows us to conclude that the assumption about the radiation hazard of some ball lightning is valid. The presented model can be checked experimentally, but safety measures should be severe. According to my model, radiation from ball lightning in the worst case can be dangerous from the distance of a few tens meters. Also, at least some of the detected gamma ray, so-called glows. Gamma ray glow is a flux of gamma ray radiation with a duration from from 1 second to a few 10 seconds, and they are detected very often currently. And the problem of ball lightning has a high political importance for fusion studies. Thank you for your attention.
We have time maybe for a couple of questions. Yes, Eric?
Thank you. Well, one of the more mysterious phenomena associated with ball lightning, which has been often observed, is the ability of ball lightning to penetrate through non-conducting walls. So would your model be able to explain this phenomenon?
Currently my model, I agree that this effect is very important, and like to note that glass cannot be considered as intact, even when it's looked in such a way. Special investigation were performed by Nikitin and his colleague of such a glass window which were penetrated by ball lightning, and they have found some small region in first of all, the glass looks like burned through by ball lightning, and sometimes the influence of ball lightning result in removal of disc of glass. So I repeat, I agree with this effect, the effect of penetration with very small observable damage of glass is very interesting, but currently I can explain this effect only qualitatively.
Okay. Thank you. Any other question, please? I have one question. When you talk about energy density as high as tens of kilojoule per cubic centimeter, right?
Yes.
Would it be possible that you have a very, very high beta plasma where the magnetic pressure is less than the kinetic pressure or thermal pressure of that plasma? Would that be a possibility? As opposed to Professor Reed's proposal of purely a strong magnetic field energy content.
He assumed that this is possible, but I can only repeat that I didn't see in his model any idea explaining compensation of this magnetic pressure. And right. I am not sure that this is possible. because in my model, the huge energy, this energy can be considered as huge because Bull lightning has density, mass density less than that of air, but its energy density is comparable with that of TNT. This results from the fact that energy is stored either by high energy, mainly by high energy electrons, or by electric fields corresponding to the situation when the electrons are far from the equilibrium position, but the kinetic energy is transferred into energy of electric field. But this energy is not associated with the creation of pressure. So I'm not sure that this is possible for magnetic fields, and initially I think that for magnetic fields this is impossible. But I did not present a large-scale calculation explaining this finding.
Okay, thank you. This is a very interesting topic, but it's I would say to me a very mysterious topic. And I also noticed that the military has conducted many unreported experimentation and measurements. So it is perhaps one day we can learn more about what they have been doing to give us more data to formulate some kind of a physical model for ball lightning. It is good to know that there is another confinement configuration, partially relying on atmospheric containment, that actually have gamma rays or hard X-rays that to the level that can damage a person's health. So you know that this is something very powerful inside. Well, with that, let's thank our speaker again.
So thank you very much for attention, and I'd like to thank organizer again for invitation.
Okay.
Thank you.
Yeah. And so I hand this session over to our local organizers. Anybody? Okay.
Later we will have lunch at the lunch there. So you can just
Downstairs.
Yes, downstairs. You can just take the elevator up there. To the first floor. So self-service.
Yeah, self-service lunch.
Yeah. And then our next session will be at 2 p.m. Please come back. Okay, so thank you. Okay.